For decades, the idea of detecting alien intelligence felt distant. Now, international scientific groups have drafted post-detection principles, guidelines recommending transparency, broad consultation, and careful handling of any discovery. But these protocols are advisory only. They carry no legal authority, and no single body exists that can enforce how Earth responds. Few outside the research community know the details of these plans, or how uncertain they would become if tested. If a message arrives tomorrow, who would actually sign off on the reply? And could humanity agree on what to say while the universe waits in silence? A universe of hidden neighbors. Why, in a galaxy filled with countless stars, have we not yet detected the faintest word from another civilization? For astronomers, this is no mere curiosity, it is a persistent puzzle. The reasoning seems almost unavoidable. If life developed on Earth, orbiting an ordinary star with ordinary conditions, then why not elsewhere? The Milky Way holds on the order of 100 billion stars. Based on findings from the Kepler mission, roughly 1 in 5 Sun-like stars appears to host a small, potentially temperate planet. That conservative ratio alone implies tens of billions of possible candidates for habitable worlds in just our galaxy. And yet, when we point our instruments outward, the silence has been total. Not one verified signal. What makes this puzzle sharper is how much progress astronomy has made in only a few decades. Until the mid-1990s, not a single planet beyond our solar system had been confirmed. The idea of exoplanets remained a hypothesis, supported only by indirect hints. That changed in 1995 with the detection of the first Jupiter-sized planet circling another star. From that point onward, the discoveries expanded rapidly. NASA's Kepler mission in 2009 revealed that planets vastly outnumber stars. Today, with instruments like the James Webb Space Telescope, the transiting Exoplanet survey satellite, and advanced observatories on Earth, this catalog continues to grow. As of mid-2025, the NASA Exoplanet Archive lists about 5,900 confirmed planets, cataloged through diverse detection techniques. And while that sounds enormous, astronomers stress that it represents only the beginning. Those represent the worlds we can see with present tools out of hundreds of billions likely to exist. Among these detections are planets that orbit in what scientists call the habitable zone, the region around a star where surface water could be stable. Others orbit faint red dwarfs, stars that make up the majority in the galaxy, where conditions likely differ but could still support biology. Each new survey reinforces the same point. Planets are not rare prizes. They are the rule. Nearly every star seems to shelter at least one, often several. For each system we can identify, thousands more must be hidden too faint or distant for us to observe. If the galaxy is populated with so many planets, then why do our surveys return silence? This contrast between expectation and evidence cuts to the core of modern astronomy. Some researchers argue that we have only just begun listening. Traditional radio searches cover thin spans of sky and brief slices of spectrum compared with the infinite possibilities. Civilizations could transmit with frequencies we are not monitoring, or employ technologies beyond our comprehension. Others raise the possibility of deliberate quiet, advanced societies choosing silence for caution or survival. A darker explanation is that the lifetime of technological civilizations is short, and most extinguish themselves long before mastering interstellar communication. Meanwhile, the astronomical hunt accelerates. With Webb, astronomers can now characterize planetary atmospheres. When starlight filters through an exoplanet's air during a transit, chemical gases leave measurable imprints. Elements such as methane, oxygen, water vapor, and carbon dioxide can all be identified. Alone, each has explanations through geology or chemistry, but combinations like large amounts of oxygen sustained by renewal raise suspicion of life. Already by 2025, certain exoplanets show atmospheric irregularities sparking international discussion. Yet interpreting these biosignatures is delicate. For example, methane alongside oxygen might suggest microbial photosynthesis, but it could also result from volcanic activity. A high-profile case this year was K2-18b, a sub-Neptune world orbiting a red dwarf. Early Webb data hinted at the potential detection of dimethyl sulfide, a compound on Earth produced primarily by biology. But independent analyses questioned the reliability of this signal, and NASA emphasized the need for extensive follow-up before drawing headline conclusions. This episode underlines a crucial point. Hints are not proof. Atmospheric patterns may point toward interesting chemistry, but science advances only with extreme scrutiny and reproducibility. This ambiguity highlights the paradox. If the statistics argue life should appear often, then somewhere intelligence should have developed, perhaps long before us. One might expect civilizations older and more advanced than ours dotting the stars. Some could have collapsed already, leaving nothing but the faintest traces. Others could endure still, spread thinly across the arms of the Milky Way. Yet to every telescope we turn, the backdrop stays mute. The stars shine, but no society announces itself. To grasp the weight of this, imagine walking through a city filled with windows, each burning with light, but hearing no movement, no voices, not even footsteps. Are the residents silently inside? Are the homes newly deserted, or were they never inhabited? This is the riddle posed by our galaxy. The silence compels us to reconsider assumptions. Maybe the conditions for life are narrower in scope than we imagine. Perhaps intelligence doesn't confer long-term survival advantages. Or maybe signals are lost in cosmic static, hidden in bands we haven't yet searched, or within complexities too subtle for current instruments to separate. Yet the evidence for planets does not go away. With every update, models incorporating data from Webb, TESS, and observatories in Chile, South Africa, and Hawaii converge toward the same conclusion. There could be tens of billions of planets in the Milky Way that qualify as plausible habitats, not just isolated rocks but stable, enduring worlds. Many orbit in configurations that allow stability for billions of years, the ingredient most necessary for evolution's long timeline. When considered statistically, our galaxy should almost certainly house biology of some kind. The unsettling dissonance comes from the gap between this expectation and our persistent null results. Each biosignature candidate sparks a burst of excitement, only to be reevaluated into uncertainty. Each signal hunt adds another stretch of silence to the tally. This is where the mystery sharpens. The data demand that planetary neighbors exist. What remains unknown is whether any of them carry life, and if so, how often that life grows intelligent. Planets are everywhere, but when we point a telescope at their atmospheres, the answers get complicated, so we built better telescopes. From Kepler to Webb, the revolution in detection. When astronomers launched the Kepler Space Telescope in 2009, it marked a decisive turn in how we study the universe. For the first time, a mission was built solely to watch thousands of stars continuously, searching for the subtle dimming that reveals a planet crossing in front of its star. The results reshaped astronomy. Planetary systems turned out to be common, not rare. By the time Kepler's mission ended, it had demonstrated beyond doubt that our galaxy is filled with billions of worlds, some perhaps rocky and temperate like Earth. But Kepler had limits. It could measure size and orbit, giving a sense of whether a planet was hot or cold, gaseous or rocky, but not what conditions were actually like on its surface. For that, astronomers needed to study atmospheres, and that required a more powerful tool. The James Webb Space Telescope brought that capability. Its large mirror and advanced instruments finally gave scientists a way to see beyond the silhouettes of planets. Webb can split starlight into spectra as it filters through a planet's atmosphere, allowing scientists to search for chemical signatures. Certain gases, such as water vapor, methane, and oxygen, absorb light at distinct wavelengths. When measured together, these gases can suggest, but not prove, that biological processes are involved. Webb can also characterize gases and temperatures on large, hot planets, and in some cases, probe smaller rocky worlds. But detecting strong biosignatures on true Earth-like planets remains extremely difficult, requiring enormous observing time and careful follow-up. What Webb provides is a step change in detail, not final answers. Ground-based facilities amplify this work. Telescopes in Chile's Atacama Desert, Hawaii's Mauna Kea, and soon the European Extremely Large Telescope contribute high-resolution spectra, revisiting and confirming Webb's early results. Space and Earth-based instruments working together now let astronomers sketch a more complete picture than ever, finding out not only whether a world exists, but also what gases drift in its skies. For certain giant planets, webcams of sorts have even traced heat patterns and weather cycles. Those cases are extraordinary, but the same precision for habitable zone Earth-sized planets is still out of reach. At most, Webb hints at patterns that raise questions, while definitive studies remain ahead. One notable example is K2-18b, a sub-Neptune orbiting a red dwarf star about 120 light-years from Earth. In 2023, Webb first detected carbon-bearing molecules, and in 2025 researchers announced a possible signal of organosulfur compounds, specifically dimethyl sulfide, or DMS. On Earth, DMS is produced mainly by living organisms in the oceans, which made the claim especially eye-catching. But within months, multiple independent teams reanalyzed the data. A NASA-led study concluded that while the signal was intriguing, it did not meet the standard for a confirmed detection. Noise, calibration effects, and complex atmospheric models make the case ambiguous. Today, the presence of DMS on KB remains very much an open question, not a discovery. This controversy underscores both how powerful Webb has become and how careful scientists must remain in interpretation. That caution matters because atmospheres can be misleading. Methane may come from volcanism instead of microbes. Oxygen can build up abiotically under certain conditions. Carbon dioxide and water vapor can mix into patterns that seem unusual but emerge from normal planetary chemistry. Webb's precision highlights these complexities, but doesn't erase them. Every potential finding has to be challenged against models of chemistry, climate, and stellar activity. The difference between a biosignature and a false signal often comes down to years of testing and replication. Still, the fact that these questions are no longer hypothetical is remarkable. For decades, discussion about life beyond Earth rested on statistics and probability. Kepler showed how common planets are, but little about their character. Webb has narrowed the inquiry, shifting debate from general possibilities to individual case studies. Instead of asking only whether Earth-like planets exist in principle, astronomers now compare spectra and ask whether one particular planet's chemical balance might resemble a living world. This is indirect evidence, still waiting for firmer answers, but it transforms distant stars into testable environments rather than vague numbers. The implications run wide. A planet with water vapor and clouds might have an active climate system. A planet where methane and oxygen coexist in the proper amounts could indicate constant replenishment, mechanisms that on Earth involve life. Detecting such patterns requires years of patient observations, but the promise is clear. Any reliable sign of disequilibrium chemistry would reshape our understanding of habitability. Even one persuasive case would change the narrative about life in the galaxy. Progress has already been steady, though slower than some expected. In its first year, Webb's instruments produced signals that were difficult to separate from noise. By 2024 and 2025, refined calibration and analysis methods improved clarity, though ambiguity remains. Coordinated campaigns between Webb and the largest ground observatories have helped eliminate false positives and confirm certain gases. Each step forward expands the catalog of promising worlds, even if biosignatures themselves remain elusive. This change in capability is historical. With Kepler, Astronomers learned our galaxy is saturated with planets. With Webb, each of those worlds becomes more than a statistic. It becomes a place with weather patterns, chemical traits, and conditions that can be contrasted with Earth's. Humanity has shifted from merely suspecting that Earth-like planets exist to identifying actual candidates and asking whether any look active, stable, or potentially alive. The objects of study are still impossibly distant, but they are no longer nameless. They are individual worlds with characteristics scientists can describe in detail. The picture remains incomplete, however. Even Webb cannot produce certainty for Earth-like planets in the habitable zone, at least not quickly. Each new candidate involves hundreds of hours of telescope time, atmospheric modeling, and often years of cautious argument. The telescope has rewritten the scale of what is possible, but the final goal, a confident detection of life, remains unsettled. That frontier is now closer, yet just out of reach. For astronomers, the shift feels less like an answer and more like a doorway. Questions once confined to speculation now take shape in data. Each ambiguous spectrum sharpens the sense of possibility, and each contested finding deepens the recognition that proof, if it comes, will not arrive easily. Even with Webb at work, the majority of planets remain silent, their fingerprints too faint for clear interpretation. And that silence raises another question. What if signals of life are not just hidden in spectra, but buried in the vast flood of data pouring from telescopes worldwide? Even with advanced instruments, many candidates remain ambiguous, slipping between noise and potential. To confront that challenge, scientists began relying on new tools, not only telescopes, but also machines built to sift through overwhelming streams of information. Even with Webb, many mysteries hold their place in static, and so the search has turned to automation and global networks to listen harder. Searching the sky with machines. For most of the 20th century, listening for signals from other civilizations relied almost entirely on direct human effort. Astronomers would point a radio dish toward the sky, collect streams of data, and then search through it either by hand or with basic computer software. The coverage was narrow, just a small patch of sky and a limited slice of radio frequencies. Yet even with this narrow focus, the sheer amount of data overwhelmed any single researcher. As detectors improved and projects expanded, the flood of information grew unmanageable. By the early 2020s, modern observatories were generating billions of possible radio signal candidates every single day. No human team could reasonably comb through such an ocean. The question became unavoidable. If people themselves could not keep up with the listening, what, or rather who, would do it instead? That burden shifted to machines. Artificial intelligence has emerged as the critical filter in the search for extraterrestrial intelligence. Rather than relying on astronomers to scan endless numbers and spectra, sophisticated machine learning models now process the torrents of radio data collected by arrays on Earth, as well as optical pulses, gathered by telescopes designed to catch brief laser flashes. These systems ingest the stream, discard the overwhelming layers of noise, and leave behind a sharper, much smaller set of unusual patterns. From billions of candidates, machines distill down to hundreds, or even fewer, that are worthy of human inspection. The method depends on training algorithms with examples of interference. Earth is dense with its own signals, satellites, cell towers, aircraft, and every kind of electronic chatter. These produce recognizable templates. By learning their shapes and timing, the machines discard them quickly and reliably. Yet the strength of machine learning rests on more than eliminating the obvious. Its greatest utility lies in anomaly detection. Whenever a burst of data refuses to fit existing categories, the system flags it. While those flags often turn out to be human-made interference or known astrophysical events, they arrive on astronomers' desks in ways that could never happen without automation. This capability is most evident in the faintest signals. Radio data often hide emissions hundreds of times weaker than the surrounding static. On top of that, Any extraterrestrial broadcast would likely drift slightly in pitch as relative motion shifts the frequency. Algorithms can monitor millions of potential frequency drifts simultaneously, analyzing the subtle shifts and extracting candidates from beneath background noise. What a human observer would miss, computational tools can catch it, turning faint anomalies into possible detections. By 2024 and 2025, such systems were no longer experimental. They had embedded themselves in the daily pace of SETI observations. One illustrative case in 2024 came from the star HIP 11915, where a persistent narrowband spike appeared in radio data. Within hours, it was traced to a bounce from a faraway communications satellite. Later that year, optical monitors flagged multiple faint flashes near Proxima Centauri. Follow-up revealed they were cosmic ray strikes on detectors. While neither proved extraordinary, both demonstrated that artificial intelligence had done its task, capturing events in real time and handing them to humans for verification. The practical interplay between machine and human has grown increasingly defined. First, an algorithm scans through countless candidates and selects a handful based on statistical anomalies. Then, human scientists step in, testing, debating, comparing the results to models, and conducting follow-up observations from independent telescopes. The most intriguing cases extend into weeks or months of review. In every instance, the process begins with machine detection but arrives at human judgment. The workflow has become essential. AI flags a ripple in the data. People decide whether it is signal, artifact, or something in between. One turning point came in 2025, when SETI engineers ran a successful demonstration at California's Allen Telescope Array. Using NVIDIA's Halaskin platform and neural networks, they processed radio streams in real time and reconstructed known pulses from a giant radio-emitting pulsar. The achievement validated that AI systems could reliably extract weak astrophysical signals directly from live data, proof that these tools are not just theoretical filters, but robust engines for discovery built into a functioning observatory. Yet the power of such algorithms comes with caution. Their performance depends heavily on configuration. Narrowing too aggressively risks deleting signals of interest before they are even recorded. The risk of false negatives is not hypothetical. Studies published in Acta Astronautica, including reviews of the breakthrough Listen pipeline, warn that certain algorithmic choices reduce sensitivity at high Doppler drift rates, the very kind of variation one might expect if a transmitter were moving relative to Earth. The lesson is clear. Machines can highlight anomalies we would never catch, but poor tuning can make the most valuable signals invisible. Every update requires rigorous validation, often inserting synthetic test signals into live data to ensure nothing is lost by accident. Unsupervised learning has added further adaptability. Rather than feeding the machine only known categories of interference, this approach lets data naturally group itself by similarity. Pulsars, microwave echoes, or atmospheric noise all emerge in clusters. What remains outside those clusters, the solitary points that resemble nothing else, become candidates. This flexibility acknowledges an uncomfortable truth. We cannot predict in advance how a genuine extraterrestrial signal might appear. Allowing an algorithm to surface the unexpected helps safeguard against too narrow an expectation of what should count as interesting. Taken together, speed and pattern recognition have altered the human role. Astronomers no longer sit hunched over piles of raw output. Instead, they wait for a report of curated anomalies. From the billions of daily events, only a short list reaches the desks of scientists who can then study them in detail. Without automation, most of that hidden subtlety would be discarded unnoticed. The reliance on machines does not replace astronomy, but it radically redefines it. This shift carries cultural as well as scientific effects. While the famous "wow" signal of 1977 became legendary through a human researcher's sudden recognition on a printout, The next truly extraordinary candidate will almost certainly come to light through a notification from an algorithm. But crucially, the machine will not decide what the signal means. Final judgment will remain firmly in the hands of human scientists and the cross-observatory checks that define responsible SETI work. Discovery, if and when it happens, will still belong to people, but people working in tandem with machines. These developments shape what discovery might look like. The first evidence of a meaningful signal will not begin with a single astronomer gasping at a chart. It will likely begin inside a machine learning pipeline, parsed, filtered, and then brought forward as a line in a log. Only then does the story shift back to human context. Observers cross-check it. Different telescopes aim their dishes to confirm or deny it. Teams argue whether the anomaly was meaningful or mundane. This sequence already reflects how searches unfold today, and foreshadows what would happen if a genuine arrival occurred. Algorithms may now form the first layer of contact with the unknown, but the path to certainty remains long, uncertain, and human-led. That creates a tension between promise and caution. On one hand, the machines give us an ear large enough to cope with the flood of cosmic data. On the other, their limitations remind us how easily potential signals could still escape. The future of SETI will depend on striking that balance, ensuring that automation empowers us without closing doors. And while AI-driven searches continue to refine themselves, the reality persists that many signals never resolve neatly. Some resist classification, sitting in the gray zone between interference and possibility. Others defy explanation long after careful review. The work of filtering provides clarity, but it cannot erase uncertainty. It is within that space of unresolved signals that the next questions arise. For all the advances made so far, the search remains shadowed by ambiguity. Signals without answers. Across decades of searching, certain signals have emerged that resist quick explanations. They stand out against the background of sky noise, not conforming to ordinary astrophysical categories, and yet never delivering proof of intelligence. Some are powerful spikes that vanish as soon as they appear. Others flare in milliseconds, gone before telescopes can turn to confirm them. A handful have repeated sporadically, but without clear origin. These unresolved detections occupy a strange middle ground, enough to hold attention, never enough to settle debate. The most famous of these remains the WOW signal. On August 15, 1977, the Big Ear Radio Telescope in Ohio recorded a 72-second burst 30 times louder than the background. It was strong, narrow, and precisely what one would hope to see if distant technology were transmitting on purpose. Astronomer Jerry Amon circled its printout with the note, "Wow," giving the signal its name. Yet in the decades since, countless follow-up observations aimed at that patch of sky have found nothing. No repetition, no confirming detection. SETI protocols now treat the WOW signal as a classic example of an anomaly, compelling enough to study, insufficient to declare evidence. That single burst set the rhythm that has followed again and again, the tension of an extraordinary signal that provides no second chance. Advances in astronomy have refined the way these anomalies are discovered. Fast radio bursts, first identified in 2007, became a regular feature of surveys. Many were traced to magnetars and other extreme astrophysical events billions of light years away. Nonetheless, some pulses displayed unusual traits, repeating in cycles or showing modulations that demanded further scrutiny. Each case provoked careful investigation, narrowing possibilities but not always closing them. They joined the growing list of signals without answers, neither dismissed outright, nor embraced as extraterrestrial communication. The question is less about proof than about process. Scientists draw critical distinctions between categories. A signal may be unexplained, surviving checks against satellites, atmospheric effects, and instrument noise, but still defying clear interpretation. That category does not mean alien, it means unsolved. Even so, unexplained signals remain a reminder that our current understanding is incomplete. Unidentified signals, by contrast, typically resolve into interference from human technology once careful tracking catches up. The challenge in practice is that these two categories start in the same place, an unusual burst flagged by machines, handed to scientists, waiting for a judgment that may never fully satisfy. Recent research has demonstrated how difficult that process can be. In 2025, the SETI at Home project, working with the Breakthrough Listen initiative, released a detailed reanalysis of archival data from the Arecibo telescope. Using modern machine learning pipelines, engineers processed billions of detections generated by the old surveys. Algorithms rapidly reduced that torrent into a more manageable short list, isolating a few hundred of the most intriguing signals that resisted conventional explanation. These candidates are now slated for reobservation using the world's most sensitive radio dish, the 500-meter aperture spherical telescope, FAST, in China. The project illustrates how a modern search operates. Automation identifies promising anomalies, and then the most powerful telescopes return to test whether any endure under scrutiny. This approach highlights both progress and fragility. Modern computing can turn seas of noise into a shortlist of serious possibilities. Yet even the best signals require follow-up across months or years, often never repeating or dissolving into patterns, eventually tied to terrestrial interference. The danger is twofold: to mistake a human source for a cosmic one, or to overlook a genuine case hidden among the false alarms. In that sense, the sharp edges of uncertainty both guide and trouble the search. The signals that remain unresolved keep open the possibility of contact, while constantly demanding safeguards against error. Each anomaly leaves behind a record that tugs at researchers and resurfaces with each new tool available. Just as the fleeting wow detection continues to inspire investigation nearly half a century later, the small fraction of signals preserved within today's candidate lists may be reanalyzed again decades from now. Machines trained with improved models may extract new details, or powerful observatories could revisit the same coordinates under better conditions. Discovery, if it comes, may follow a path from anomaly to archive to rediscovery before finally reaching consensus. For the public, the ambiguity is both frustrating and magnetic. Stories about single bursts or unusual patterns circulate widely, often outpacing the careful caution of scientists. Research teams work slowly, revisiting data, publishing provisional results, inviting other groups to confirm or dispute them. The debate takes years. Meanwhile, the curiosity persists. Could communication first arrive not as a decoded message, but as an unresolved candidate? What if the first evidence of others is less like a conversation and more like the wow printout, a strange trace left behind, daring us to interpret? That possibility reshapes how we think about discovery. A verified signal would be transformative, but the road there may never be straightforward. It might begin not with clarity, but with faint irregularities that resist elimination. A whisper of statistical significance, barely distinct from natural activity, could linger until a crucial reobservation finally tips consensus. The uncertainty itself becomes part of the story. The recognition that the line between anomaly and contact is thinner than most imagine, which raises the real possibility. The first contact, if it comes, may begin not with a clear broadcast, but with a candidate that refuses to go away. From there, the question shifts outward. If ambiguous signals keep challenging us, how do institutions, governments, and the broader public respond when confronted with mysteries they cannot fully explain? Unidentified aerial phenomena and public disclosures. In recent years, unidentified aerial phenomena, UAPs, as agencies now call them, have shifted from closed military files into open public discourse. What was once dismissed as rumor or fringe speculation is now treated with seriousness by governments, scientists, and the media. Official press briefings, public reports, and interagency panels have reframed the issue. In effect, official silence turned into official study, and that shift changed who reports sightings and how they are handled. This cultural change gained momentum through disclosures that emphasized method rather than mystery. In the past several years, NASA convened independent experts to review UAPs and other interagency bodies, including the All-Domain Anomaly Resolution Office and the Office of the Director of National Intelligence, published reports. These efforts did not claim to resolve the phenomenon. Instead, they urged standardization, how to collect sightings with calibrated instruments, how to combine radar with optical evidence, and how to archive reports for independent review. Their central message was methodological. Better data and reduced stigma were more important than dramatic conclusions. By highlighting accuracy and openness, they marked a departure from decades when witnesses, including military pilots, hesitated to come forward. Similar processes unfolded outside the United States. In Europe, defense ministries released partial footage and radar returns from pilot encounters, drawing attention to aircraft performing maneuvers that strained conventional explanations. Officials stressed that their purpose was not to suggest extraterrestrials, but simply to show which cases remained unidentified. Across parts of Asia, governments acknowledged their own investigations, in some instances with participation from universities. Such confirmations carried weight, since radar networks from different nations had registered anomalies at overlapping times. When countries with competing interests agree that an aerial event was unidentified, speculation about fabricated evidence grows far less persuasive. Still, much of the material provided to the public remains incomplete. Reports arrive with thick redacted passages, and only short segments of video are sometimes released. Higher resolution data, detailed radar logs, sensitive imaging, and full pilot testimonies often remain classified. Agencies argue that concealing this information protects sensor capabilities, intelligence methods, and national security. Revealing the full scope of detection technologies, they insist, would hand adversaries a blueprint to exploit vulnerabilities. From the standpoint of governments, secrecy is strategic. From the standpoint of the public, secrecy perpetuates suspicion. That gap has set the tone for nearly every major disclosure, a mix of revelation and withheld detail. For scientists, this partial transparency makes interpretation difficult. A compressed video of a fast-moving light may hold too little detail to judge whether it shows an ordinary aircraft, an atmospheric effect, or a physics-breaking maneuver. Radar plots in summary form cannot reveal whether anomalies come from an object's motion or instrument limits. This often leaves researchers debating less about what UAPs are and more about what the evidence itself can support. Complete transparency remains rare, but the fact that scientists are even invited into discussion represents a departure from decades of marginalization. The relationship between UAP studies and traditional SETI research demands careful clarity. Both concern unexplained phenomena, and both involve broad public curiosity about life beyond Earth. But the methods differ fundamentally. UAPs are tracked within Earth's atmosphere, studied mostly by defense agencies and intelligence offices. SETI, by contrast, scans the sky for technosignatures, radio pulses, optical flashes, or atmospheric markers, using astronomical protocols designed for distant observation. Conflating the two risks misunderstanding both. They overlap in public imagination, but they remain distinct scientific and institutional domains. Still, it is undeniable that UAP disclosures affect how the public perceives SETI. Hearing officials confirm encounters with unidentified aerial objects makes society more willing to take the broader search for intelligence seriously. Each pushes people toward the same fundamental recognition. The world remains full of mysteries we cannot yet explain. When governments acknowledge unexplained data openly, space scientists gain clearer ground to explain why sustained searches for extraterrestrial signals deserve investment. This changing climate has also altered stigma. For decades, pilots hesitated to file reports, fearing ridicule or damage to career reputation. Scientists discouraged colleagues from attaching professional standing to the subject. With the rise of formal panels, that dynamic shifted. Witnesses now have channels to record their experiences without stigma. Data can be archived rather than dismissed. Even when further analysis explains a case as a balloon, a drone, or instrument noise, the process itself is more rigorous. Removing ridicule from investigation has made anomalous data easier to study. And that change matters. A system that respects pilots and scientists when they report anomalies is one more likely to recognize genuine breakthroughs if they emerge. Public reactions have reflected a wide spectrum. Some interpret redacted reports and selective video as signs that officials conceal extraordinary truths. Others dismiss the events outright, demanding stronger evidence. The scientific community works in the tension between these stances, calling for patient accumulation of data rather than premature conclusions. The result is a public conversation marked by cautious progress, moving forward, but inevitably slowed by limited evidence and competing interpretations. By 2025, the overall picture has become paradoxical. Governments disclose more than ever, yet retain secrecy. Scientists gain recognition in the conversation, but lack full data sets. Citizens show heightened awareness but divide sharply about interpretation. Unidentified aerial phenomena rest at the intersection of science, national security, and public trust, a juncture that resists easy resolution. Each disclosure advances transparency, while each withheld record sustains suspicion. Nevertheless, one outcome is already clear. UAPs have forced institutions to acknowledge the unknown openly. NASA, which for decades concentrated solely on planetary science, now speaks directly to the question of aerial anomalies. The Pentagon and allied agencies admit collections of pilot encounters that once sat buried in classified files. International partners compare notes on overlapping radar events. The phenomenon has not proven contact with another civilization, nor reshaped our scientific worldview overnight. But it has changed the patterns of communication. Arguments once confined to rumor now play out in televised hearings. Questions that once carried stigma now appear in official logs. This transformation extends beyond the possibility of extraterrestrial explanation. UAP disclosures reveal that governments and science institutions are gradually preparing themselves, and the public to confront uncertainty directly. They show that secrecy and openness compete in shaping the narrative, but openness is advancing where silence once dominated. Whether the objects themselves resolve into drones, undiscovered weather effects, or still unknown technology, their role in history is already established. They shifted institutional culture from dismissal to study. Yet this broader recognition leads naturally to another concern. As mystery in the skies becomes normalized, so does the realization that unresolved phenomena could demand coordinated responses. Acknowledging the unknown is one step. Deciding how humanity should react if a definitive signal or contact someday arrives is another. And that question opens a far more difficult conversation. Who decides the first reply? If the universe did answer with a signal, the next challenge would not be detection but decision. Who has the right to verify it, to announce it, and to draft humanity's first reply? These questions sit at the boundary of science and politics, and they reveal how fragile our current preparations remain. Verification would be the essential first step. The SETI community operates under a set of post-detection principles known as the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. These guidelines recommend that no single observatory or team declare discovery on its own. Instead, any candidate signal must be verified through independent confirmation, ideally by facilities on different continents using different instruments. Only when another observatory records the same transmission under comparable conditions does the candidate move closer to being accepted as genuine. In practice, this process involves days or sometimes weeks, depending on telescope schedules and availability for follow-up. Radio arrays must reorient toward the target, optical telescopes must rule out natural or stellar sources, and every possible interference from satellites, military activity, or aircraft must be eliminated. The reasoning behind such caution can be seen in multiple historical cases. Candidate detections in the late 20th century, signals that looked exotic at first glance, often turned out to be terrestrial interference upon closer analysis. More recently, radio bursts once suspected of being unusual techno signatures were traced to microwave ovens and other local sources. These false alarms showed how easy it is for extraordinary claims to emerge from ordinary mistakes. This is why protocols emphasize replication, verification, and transparency. The process does not exist to produce headlines quickly, but to prevent the wrong announcement from being cemented as fact. Once a strong candidate survives verification, communication becomes the next concern. Protocols state that the detection team should promptly inform the wider scientific community and the public, typically through coordination with the International Astronomical Union and other recognized networks. The idea is to avoid a lone observatory holding a press conference before the evidence has been vetted, which might produce panic or misinformation. A coordinated statement would explain the nature of the signal, describe who confirmed it, and outline the next phases of investigation. The principle is not global secrecy, but global clarity. Yet this ideal faces clear obstacles. In a world of rapid news cycles, governments or institutions may see political benefit in announcing the discovery on their own terms. The question of reply proves even more complicated. Draft guidelines often suggest that if a message appears deliberately aimed at Earth, the matter should be taken up by international discussion bodies, with the United Nations acting as a forum for organizing debate. But there is no binding treaty that grants the UN controlling authority. Recommendations can be made and panels can be convened, but sovereign states retain the right to act independently. This leaves an unresolved gap. Global protocols encourage collective decision-making, but nothing in law prevents a nation from transmitting a response on its own, regardless of whether others object. Geopolitics makes this divide even clearer. Scientific practice favors collaboration. Data from projects like Breakthrough Listen or the arrays in Australia and South Africa are often shared freely across borders. But when the subject shifts from searching to answering, the balance of incentives changes. Sending the first words of humanity is no small act. It carries immense symbolic influence. If space exploration has repeatedly been framed in terms of national prestige, then first contact would only amplify that competition. The nation or institution that drafts and sends the initial reply could be seen as humanity's representative, claiming a position of authority in a domain no previous power has ever held. Examples from history illustrate how easily science becomes entwined with competition. The launch of Sputnik was not simply a technical achievement, it was a political act that triggered the space race. The landing on the moon, though supported by scientific goals, was for decades a symbol of Cold War competition. In this light, the idea that a first reply to an extraterrestrial message might be contested by rival governments is not merely speculation. It follows a pattern we already know. The protocols and advisory bodies may recommend cooperation, but national interests may drive division. In recognition of this tension, discussions under the International Academy of Astronautics and similar forums have created task groups dedicated to post-detection planning. These groups bring together scientists, policymakers, and communication experts to outline procedures for verifying candidates and guiding announcements. Their reports emphasize openness, careful communication, and international coordination. But the limitations remain. These guidelines offer structure, not binding authority. They cannot compel adherence. They rely on voluntary compliance, and any government determined to act independently could do so. This is why many experts stress that protocols prepare us methodologically, but politically we remain uncertain. The challenge extends beyond structure to content. If humanity does choose to reply, what should we say? Various draft concepts have been proposed over the years. One approach is to begin with minimal messages, mathematical sequences, representations of prime numbers, or binary codes that convey logic and structure without specific cultural information. Another approach includes symbolic summaries of biology, such as representations of DNA or planetary coordinates. More ambitious proposals suggest transmitting vast digital archives of human knowledge, but every option raises concerns. Would presenting ourselves as purely logical thinkers mischaracterize us? Would revealing biological and planetary data expose us to unnecessary risks? Would sending curated cultural samples represent who we are, or who a small group of designers want us to appear to be? None of these questions have agreed-upon answers. Security concerns only intensify the debate. Some argue that transmitting our location and biological details could be hazardous. They point out that we know nothing about the intentions of whoever is listening, and caution that drawing attention to ourselves might invite risks beyond our imagination. Others counter that the very act of receiving a message implies the other side already knows we exist. In this view, silence might be interpreted as indifference or hostility. The divide between caution and openness mirrors older debates in human history about how to engage with the unknown. Both perspectives recognize the gravity of the act, but disagree on which path best secures the future. Even within scientific and policy circles, these unresolved divisions remain sharp. Astronomers may prefer to delay a reply until wide consultation has occurred, while some governments might see advantage in acting quickly. Media organizations may break news before verification is complete, pushing policymakers into reactive decisions instead of measured deliberation. In short, even with decades of preparation, the practicalities of the first reply collide with political realities. The briefest signal from space could ignite a global contest of authority, prestige, and narrative control. As of 2025, humanity therefore stands prepared only in part. We have principles that explain how to check and confirm a detection, and we have coordinating bodies ready to help frame announcements. But there is no formal structure that compels nations to answer together, nor any agreed script to define what our response should contain. The decision of how, or whether, to reply remains suspended between scientific ideals of transparency and political instincts of competition. It is a problem we can describe clearly, but not yet solve. And so the possibility lingers. The first signs of another intelligence might not come as biology at all, but as traces of technology, markers of engineering or signals of construction beyond natural explanation. Just as the question of who replies remains unsettled, so too does the scope of what evidence we should even expect to find. Techno-signatures, traces of civilizations. What if the first evidence of advanced life appears not through fossils or microbes, but as the mark of technology itself? For decades, astronomers concentrated on biosignatures, chemical traces of activity resembling life. Yet intelligent societies, if they survive long enough, could leave far stronger beacons through their engineering. These intentional or unintentional traces are called techno-signatures. They include radio transmissions, coherent bursts of light, atmospheric pollutants, waste heat, or even colossal orbital structures. Each represents not biology but technology visible across interstellar distances. Radio leakage was the earliest techno-signature under consideration. Earth itself has been radiating sound and images into space for roughly a century. Radar sweeps, television broadcasts, navigation signals, satellite uplinks. All of it spills outward in a faint sphere of radio energy expanding at the speed of light. A parallel zone of leakage from another world might be detected as a narrowband signal, a frequency far too clean and sustained to be natural. Surveys such as Breakthrough Listen continue to monitor for this kind of emission, but SETI researchers now accept that not every civilization will communicate as we did in the mid-20th century. Relying on radio alone risks missing other, possibly more durable, technological footprints. One prominent candidate is the megastructure. Astronomer Freeman Dyson famously suggested that a highly advanced civilization might construct vast swarms of satellites to capture a star's energy. Such a Dyson swarm would divert starlight and irradiate its energy as heat, leaving a distinctive signature, a star that appears dimmer in visible light, yet unusually bright in infrared. In the mid-2010s, the star KIC 8,462,852, better known as Tabby's star, exhibited highly irregular dimming events that drew global attention. Some speculated about alien engineering, while most astronomers pointed to dust clouds and natural variability. Subsequent studies favored natural explanations, but the episode demonstrated the principle. Stellar light curves can act as Techno signature candidates, even if most anomalies resolve into astrophysical phenomena. Researchers now incorporate such lessons into wide surveys, knowing unusual dimming might reveal natural processes or something engineered. Another focus lies in synthetic gases. Our own atmosphere has shifted drastically within a short span due to industrial activity. Compounds such as chlorofluorocarbons, which are industrial in origin, leave sharp spectral lines. If detected in significant amounts in a distant planet's atmosphere, they would represent chemical evidence of technology. Instruments like the James Webb Space Telescope already separate planetary light into fine spectra. Upcoming platforms, such as the European Extremely Large Telescope, will reach even higher precision. Models now predict how artificial molecules would appear in data and how to discriminate them from natural sources. Researchers stress that no detection has been made yet, but the capacity is new. For the first time, telescopes are sensitive enough to start looking for unequivocal industrial fingerprints on alien worlds. Lasers introduce a different pathway. Coherent light pulses can travel immense distances with less dispersion than radio. A civilization might use lasers to communicate directly, transmit energy, or even signal deliberately to others. Recent projects like Laser SETI and the long-running Harvard Optical SETI surveys have monitored the sky for nanosecond bursts of light too sharp to originate naturally. Detectors spread across observatories look for coincident flashes, ruling out cosmic rays or instrument glitches. So far, no confirmed signals have emerged, but the methodology has matured. Where natural astrophysics rarely creates a clean, split-second pulse, a genuine detection would stand out with clarity. As hardware improves, astronomical data archives are also being revisited for missed patterns. Waste heat provides another important signature. Energy cannot be used without releasing some portion of it as thermal radiation. A civilization running on planetary or stellar scales would create excess infrared glow far above natural levels. Surveys using the Wide-Field Infrared Survey Explorer and its successors have scanned the skies for stars or galaxies exhibiting such mismatches. Some candidates showed excess mid-infrared emission, but most were resolved as ordinary dust, active galactic nuclei, or star formation regions. A few remain under review, illustrating the balance between promise and false positives. High-resolution radio imaging and follow-up studies have ruled out several supposed Dyson sphere candidates, underlining that rigorous checks are essential. Still, the methodology has become routine, searching the infrared sky for greenhouses of power too bright to be natural. Researchers have even considered unconventional messengers. Neutrinos, nearly massless particles that slip freely through matter, are studied at facilities like IceCube in Antarctica. Because so little interferes with them, Some theorists proposed that a civilization might use neutrinos to signal across great distances. In 2020, a high-energy SETI white paper argued that while dedicated neutrino messaging programs are impractical with today's resources, commensal use of existing detectors could allow rare but meaningful searches. This approach accepts that while the probability is low, the possibility is profound. Neutrino SETI is unlikely to find a message soon, but the conceptual framework reminds astronomers that technosignatures may exist far outside familiar wavelengths. By 2025, technosignature research now stands as the broadest in history. Traditional radio SETI continues, tuned to channels like the hydrogen line near 1.4 GHz. Alongside it, optical observatories watch for ultra-fast flashes, infrared surveys hunt for energy-intensive civilizations, and atmospheric spectrographs scan for pollutants unique to technology. Computational methods knit these lines of evidence together, asking whether a star with strange dimming also flickers with narrowband radio, or if a planet with alleged biosignatures also glows unusually bright in mid-infrared. The diversity of tactics reflects humility. We cannot guess what technologies others might adopt, so we test many channels at once. Concrete cases illustrate both value and warning. Tabby's star showed how a natural process could mimic megastructure predictions. Confusing pollutants have appeared when telescope calibration or stellar chemistry was misread. The brightest infrared anomalies often come from dust clouds rather than hidden engineering. At every step, researchers caution. Most technosignatures flagged are eventually explained by astrophysics. False positives are inevitable, but each helps refine methods and avoid premature declarations. That, too, is discovery, learning the limits of nature while maintaining vigilance for what might remain. The expansion matters because it reframes the question. Once we looked only for civilizations beaming strong radio signals directly at Earth. Now we consider that their presence may instead lie in waste heat, industrial smog, or fleeting optical flashes. In 2025, this broad program is still young, but each survey builds resilience against missing an encounter simply because the method was unexpected. Instruments cross-reference, algorithms highlight subtle outliers, and astronomers reconsider what counts as evidence of technology. With this framework, technosignatures remind us that alien contact may not come as a deliberate greeting. It could appear as a side effect of progress, heat concealed in the spectrum of a star, unearthly molecules preserving themselves in thin air, or unexplained bursts of exacting light. Each is a potential shadow of civilization. In this expanding network of searches lies the most ambitious effort yet to notice another intelligence, not by waiting for an invitation, but by reading the marks left behind. That recognition opens a broader dilemma. If we are prepared to detect the presence of another intelligence, should we also consider sending evidence of our own? Some researchers argue that waiting quietly is safer, while others maintain that we should broadcast boldly. The debate turns less on what we are able to see and more on what we ought to say. The ethics of contact. The ethics of contact take us beyond technology and into questions of responsibility. At issue is not just whether signals can be detected, but whether humanity should deliberately act to make itself known. This is where scientific methods meet philosophy and politics, and where disagreements often run the deepest. Core of the debate has long revolved around active SETI, also known as messaging extraterrestrial intelligence. Supporters argue that waiting passively is not truly neutral, while opponents insist that broadcasting is a dangerous act carried out without full global consent. On one side stand those who want to transmit, believing communication is the logical extension of searching. On the other side are those urging caution, warning that such actions may create risks beyond our ability to evaluate. Both sides acknowledge the enormity of potential contact, but they disagree on whether the first move should be ours. Advocates of broadcasting point out that Earth is already visible. For nearly a century, our planet has leaked energy into space. Radio, radar, and television signals radiate outward each day. This, they argue, means our cover has already been broken. To them, sending a deliberate message would not increase the danger, but would instead allow us to define ourselves in a controlled and purposeful way. In fact, some researchers, including members of the SETI Institute, emphasize that leakage already reveals us up to limited distances, which suggests that deliberate signals likely add little new risk. Advocates see silence as a less honest stance. It pretends concealment is possible when in practice, a faint but steady beacon has already gone out. Critics see things differently. Faint leakage is not the same as a targeted, powerful signal sent across light years. Leaked broadcasts dissipate quickly, blending into cosmic static. Purposeful transmissions, however, could cut through that noise and reveal precise details. Our planet's location, our technological capacity, and our willingness to engage. Those urging silence argue we cannot know who might be listening, nor can we guess at their intentions. Contact with a much older, more advanced civilization would almost certainly favor the other side. Stephen Hawking's repeated warnings loom over this discussion, cautioning that history offers too many examples where unequal encounters led to exploitation or collapse of the weaker party. Critics believe risk, however remote, cannot be justified in the absence of consensus. Both positions bring their own historical analogies. Supporters imagine the benefits of connection, shared knowledge, scientific transformation, and cultural inspiration. Opponents point to lessons from our past where discovering others often meant conquest. The comparison is not perfect. No empire has ever bridged light years, but it underlines the uncertainty we face. With no precedent, both sides rely on speculation, weighing hope against fear without firm ground. Even if one accepts the idea of transmitting, the next question is content. What should we actually send? Previous efforts provide several models. The Arecibo message of 1974 encoded numbers, atomic structures, and a human figure. The Voyager Golden Records offered music, greetings, and scientific diagrams. More recent conversations have considered uploading cultural archives, texts, images, or snippets of Earth's internet. Some suggest sending the complete genetic code of humans as a literal blueprint of our species. Each proposal is framed as a gesture of introduction, but each risks presenting a distorted or dangerous picture. Here the ethical concerns deepen. A digital archive might overwhelm or confuse, illustrating a fragmented and chaotic society. Raw internet samples could reveal aggression, inequality, and conflict as much as art or science. Genetic maps could expose vulnerabilities. Even the simplest act, showing mathematics or planetary coordinates, carries a declaration of who we are and what we can do. Opponents argue that no group can rightfully decide what defines humanity for others. To transmit anything without broad discussion risks misrepresentation, offering a single view of our world as though it were universal. Representation is therefore as pressing as risk. The post-detection principles often cited by SETI communities recommend that no message should be sent without broad international consultation. The Declaration of Principles explicitly states that any reply ought to reflect global input rather than a unilateral decision. Yet these guidelines are advisory, not binding. In practice, no international body can enforce them. Individual researchers, private organizations, or even governments remain free to act independently. The lack of enforceable authority leaves the door open for fragmented voices to declare themselves as representatives of Earth without consensus. Some experts have sought tools to quantify potential consequences. The San Marino scale, for example, evaluates attempted transmissions by weighing their strength, content, and likelihood of detection from afar, comparing them with natural background leakage. It provides a framework for rating risk and significance, though like all such systems it cannot eliminate uncertainty. What it demonstrates is an attempt to move active SETI beyond intuition and into a structured assessment where benefits and dangers can be weighed systematically. Still, like the Declaration, its influence lies in guidance, not enforcement. Today, projects continue in both directions. Small groups send symbolic broadcasts, signals directed toward nearby stars, often more demonstrations than serious attempts at dialogue. Others invest in listening only, refusing to condone outbound messages until stronger safeguards and agreements are in place. Scientific academies issue position papers, while the United Nations has convened workshops, but no resolution has emerged. As of 2025, humanity remains divided, and the standoff continues: boldness versus restraint. In this unsettled state, the problem of representation grows sharper. Suppose a signal were sent and received tomorrow. What would it mean if humanity's first words came not from a collective voice but from one laboratory or one nation, acting independently? Could a few people legitimately declare that they speak for billions? Would other nations, other cultures, or other generations accept being represented this way? Active SETI highlights this unease. The awareness that a choice so large might belong to all, yet could be claimed by the few. Underlying the entire debate is recognition of responsibility. A message transmitted today may travel for centuries before arriving, and the consequences would land on descendants who never took part in the choice. Is it ethical to bind future generations to risks created by our curiosity? Or is it unethical to withhold the chance of connection because of fears they might never share? The paradox is clear. Silence and speaking both carry costs, both involve speculation, and neither can be proven right by evidence we currently possess. The current landscape shows how fragile the consensus is. Scientists and policymakers argue, but the matter is not resolved. International forums call for restraint, but enforcement is absent. Private efforts go forward, knowing they cannot be stopped, and critics lament the absence of any unified control. What unites all sides is acknowledgement of the stakes, the possibility of altering not only how humanity is seen, but how it survives. Who gets to decide? Scientists, diplomats, or the whole planet? There's no simple answer, and that makes the question profound. And looming just beyond this debate is an even more practical tension. If a signal does arrive, then beyond philosophy, humanity must face the concrete problem of response. Some argue discovery would force cooperation. Others fear it would trigger rivalry. The possibility of alien contact does not only test ethics, it tests the capacity of nations to work together, or to compete, when the stakes extend across the stars. Cooperation or competition. The moment a signal from another intelligence is confirmed would force humanity into its most difficult collective choice: to treat the discovery as a shared heritage or as a prize to claim. Cooperation holds the promise of a planetary voice, a rare chance to meet the unknown without national divisions. Competition, however, offers nations the lure of prestige, power, or secrecy. In such a situation, unity and rivalry would press against each other, and which one prevails would shape the first response ever made to beings beyond Earth. In scientific circles, cooperation has long been the starting point. SETI communities drafted post-detection principles decades ago, with the expectation that any candidate signal should be verified by multiple observatories, and then released promptly for global review. Data are meant to be open, interpretations collaborative, and announcements guided by international networks such as the International Astronomical Union. More broadly, scientific work in this area already demonstrates that cooperation is possible. The AlienLife telescope array was designed with international partnerships in mind. Breakthrough Listen publishes large datasets openly for researchers worldwide. And the SETI at Home project invited millions of volunteers across nations to contribute unused computing power. Together, these efforts create a precedent of openness. In parallel, even government-led investigations into UAPs, through the Office of the Director of National Intelligence, and the All-Domain Anomaly Resolution Office reflect a move toward greater transparency, even if uncertainty still dominates the evidence. But these frameworks rest on trust, not enforcement. Nothing compels a nation to abide by scientific guidelines if it believes an advantage is possible. The protocols do not carry the weight of law, and governments are free to keep or disclose information as they see fit. In theory, discovery would unfold through careful verification, open data, and transparent announcements. In practice, the first team to capture a signal would hold immense political weight, and with it, the temptation to declare discovery independently. History shows that moments of great symbolic importance, whether the first satellite in orbit or the first footprint on the moon, create opportunities for countries to stake prestige. Announcing proof of another civilization could carry even greater influence. The struggle between cooperative ideals and competitive instincts has already left its mark in space history. During the latter half of the 20th century, Sky and Telescope and other outlets chronicled how spaceflight became both a scientific milestone and a theater of political rivalry. The Cold War space race measured national power through missions and achievements, each step a demonstration of technological superiority. In contrast, later projects such as large ground-based observatories drew funding and expertise from multiple continents, showing how shared goals could unite rather than divide. Both trajectories underline the same truth: politics never leaves the room. Scientific achievement may be global in principle, but prestige feeds rivalry. A signal from another world would magnify this tension unmistakably. Ownership of discovery is one of the most obvious flashpoints. Radio telescopes are national assets. If the first faint pulse appears on a dish funded, staffed, and operated by a particular country, who controls the release of data, post-detection guidelines argue for international confirmation before any announcement. But governments may calculate that waiting allows rivals to share in the prestige. That calculation could tilt disclosure toward secrecy, at least in the immediate aftermath. A confidential review process might be justified as security, but it would easily blur into claims of ownership. Symbolic gains are rarely surrendered voluntarily. Another layer of rivalry could emerge in the interpretation of the signal itself. Decoding a transmission would demand expertise across disciplines: linguistics, mathematics, cryptography, and more. Teams would form globally, but partial results would likely appear first in localized circles. A nation in possession of early fragments could retain them, citing caution about sensitive knowledge, or could use them as leverage to influence international decisions. Even if no military or technological secrets exist within the message, the possibility that they might be hidden there is enough to justify secrecy. Every step of the decoding process would balance cautious openness against the fear of strategic loss. Differences in political culture make unified action even harder. Some governments emphasize secrecy in surveillance and defense. Others operate with traditions of transparency. Some view international organizations as central authorities, while others treat them as secondary to sovereignty. These differences mean that a signal, once detected, might prompt varied and contradictory responses. One government could delay release, another could publish quickly, a third could carve out selective access for allies. Scientists advocating open sharing might push against governments determined to restrict information, creating tension between professional norms and political realities. Practical incentives reinforce those divisions. Governments fund nearly all large-scale astronomy projects. A discovery could justify higher budgets for research or defense, and with those budgets comes public prestige. A country could argue its leadership was vital for humanity's greatest discovery, using that claim to bolster its global image. In this sense, extraterrestrial intelligence could become less a shared revelation and more a political instrument. Even scientific benefits might become bargaining chips in negotiations. Cooperation sounds ideal, but when resources, attention, and influence are at stake, Competition often proves the stronger force. Yet the counterweight to rivalry lies in the scale of what would be revealed. Discovering that humans are not alone reframes identity itself. National disputes might narrow in importance compared to a universe suddenly shown to contain others. For scientists, this larger perspective already drives cross-border work. Shared telescopes, multinational exoplanet surveys, and open-access publications demonstrate that cooperation in practice exists and can flourish. These structures do not erase politics, but they provide a framework for resisting the immediate pull of national advantage. Still, whether they hold under the most intense pressure imaginable, the proof of alien intelligence remains unresolved. If such a moment came now, the first stages might still reflect cooperation. Independent observatories would confirm detection. Scientific bodies would coordinate announcements. International institutions such as the UN could convene discussions. But beyond those initial procedures, the unity could waver quickly. Governments would soon debate how to interpret the content, whether to reply, and who held the authority to decide. At that point, the precedent of shared verification might give way to familiar political divides. The cooperative framework offers a path, but it does not guarantee it will be taken when power, prestige, and fear are at stake. The scientific protocols and UN-linked discussions represent humanity's best attempt to prepare. They are thoughtful and precise, but they remain advisory. Their effectiveness depends on voluntary compliance. History suggests that voluntary compliance can falter at pivotal moments. Cooperation in space is possible. It has delivered remarkable achievements. Rivalry in space is also persistent. It has driven competition since the earliest rockets cleared the atmosphere. If something as profound as contact with another intelligence were to occur, both tendencies would come to the surface, shaping every step of the response. The choice between collaboration and rivalry is therefore more than procedural. It is a question of whether humanity can align around a discovery that transcends nations, or whether the oldest instincts of competition will define the moment. Protocols envision cooperation, but history warns about prestige and secrecy. The answer is unclear, and perhaps it always will be until the moment arrives. If cooperation can fray under pressure, can we realistically expect a united response in the narrow window that matters most? Or will national rivalry decide the first words humanity sends to the stars? How likely is contact in our lifetimes? The pace of the search naturally leads to a pressing question. What are the odds that any of us alive today will see contact happen? Predictions vary, but they remain anchored in the tension between how much progress has been made and how much mystery still holds. Some look at the scale of discovery in the past few decades and conclude that we are approaching a turning point. Others believe that even with rapid advances, the silence so far indicates a much longer wait, possibly far beyond our lifetimes. The outcome hinges on how the unknowns balance against what is becoming measurable. Optimists point to the breakthroughs that have reshaped astronomy since the early 1990s. What once felt speculative now carries hard numbers. The NASA Exoplanet Archive lists about 5,900 confirmed planets as of mid-2025, drawn from missions like Kepler, TESS, and the James Webb Space Telescope. From these, astronomers estimate tens of billions of habitable zone planets exist in the Milky Way alone. On such scales, they argue, life cannot be unique to Earth. SETI Institute researchers and other leaders in the field have even ventured predictions that detection could come within decades, fueled by improved computing, wider global surveys, and the rise of artificial intelligence handling data floods. They suggest the silence is temporary, an artifact of how little sky and spectrum we have actually tested. Pessimists counter with the Fermi paradox. If civilizations are common, why has the universe so far offered no clear evidence? They argue this absence might not be coincidence but signal. It could be that life rarely passes into complexity, or that intelligence almost always proves brief in cosmic time. Some invoke the idea of a great filter, a step in the progression from planet to technology that is so improbable or destructive that very few worlds make it through. In that view, our existence may be rare precisely because most civilizations collapse long before they develop the stability to send signals across light years. For these voices, the silence is not simply a limitation of our search, it may be the message itself. This divide is often framed using the Drake equation, an attempt to capture the full chain from star formation to technological society. Many terms are now constrained by data. We know about how many stars form each year in our galaxy. We know nearly every star has planets. Kepler's census and later surveys give ranges for how many of those planets fall into habitable zones. But the biological terms remain wide open. How often does life actually spark? How often does it climb into complex intelligence? And above all, the final Drake variable, L, the longevity of civilizations, resists any measure. This term is the most uncertain of all, yet it determines whether many civilizations overlap in time. If L is short, then even if life is abundant, contact is unlikely. If L is immense, then the galaxy should overflow with signals. At present, we lack the evidence to decide which is true. Within that uncertainty, microbial life seems the more likely discovery in the near future. The detection of biosignature gases is edging closer to plausibility. Webb has already provided atmospheric spectra for a handful of exoplanets, and the coming generation of ground-based giants such as the extremely large telescope will sharpen that capability. Identifying methane paired with oxygen or other chemical imbalances could imply life at work. If the pace of improvement holds, many astronomers believe that by the late 21st century, or possibly much sooner, we will detect persuasive evidence of biology elsewhere. It may not be intelligence, but it would still mark the crossing of a threshold no previous generation achieved. Signals from intelligent societies pose greater difficulty. Here the pessimists find stronger footing, since the data yield no verified examples despite half a century of listening. Yet optimists stress how limited those searches have been. Radio SETI so far has sampled a tiny fraction of frequencies, often for short durations. Optical SETI and infrared Techno signature studies are even younger, barely touching the surface of possibilities. And new forms of analysis, using machine learning to parse billions of daily radio detections, are only now scaling effectively. In this sense, humanity's search could be compared to dipping a cup into the sea and concluding there are no fish. Expansion in frequency, sensitivity, and duration must precede stronger conclusions. Philosophy of time also shapes the debate. A civilization lasting 1,000,000 years would scan across eons, while one lasting only 500 years might appear as a faint blip before fading. Whether detection occurs in our lifetimes depends less on abundance than on coincidence, overlap in time, as much as overlap in space. We may have been early, arriving before neighbors rise, or late, arriving after they vanished. Synchronization, rather than probability alone, may explain why so little has been seen. For now, both camps coexist. Optimists invoke the immense numbers of planets as weight in their favor, coupled with the accelerating power of detection tools. Pessimists reply with the stark fact of silence, arguing that no matter how great the numbers look, they mean little without verification. Both attitudes shape ongoing funding and public interest. Predictions often mirror philosophical leaning more than strict calculation, because the decisive variables remain hidden. The question becomes less one of raw numbers than one of expectations. Should we see life in a human lifetime, or should we prepare for the long silence of deeper time? The most balanced outlook accepts both possibilities. Within several more decades, biology may be confirmed elsewhere, likely through atmospheric chemistry rather than direct images of alien creatures. Intelligent contact is harder to project. We may live to see it, or the search may extend indefinitely, with each generation building sharper tools yet still finding only silence. The uncertainty itself reflects the frontier of knowledge. A universe proven full of planets, but quiet of voices, may yet conceal profound discoveries waiting within the noise. Even if we never hear a voice in our lifetimes, the next few decades are poised to answer a simpler question almost as profound. Is life itself common in the universe? That answer, when it comes, will carry weight regardless of whether intelligence joins it. And with every step closer, the act of searching continues to confront us with questions not just about others, but about ourselves. In the end, what the search reveals most of all is how humanity chooses to define its place in a universe of possibility. Whether a signal arrives tomorrow or centuries from now, the search has already changed how we think about our place in the universe. Discoveries of planets, strange atmospheres, and unexplained signals place Earth within a far larger context, reminding us that we are part of something vast and unfinished. The unresolved question is survival. In the Drake equation, the final term, L, the longevity of civilizations, remains the most uncertain. If others endure, their persistence is what allows contact, and that reflection turns inward. Our greatest responsibility is ensuring we endure long enough to join the conversation. Tell us in the comments, if we got a signal tomorrow, what would you want the world to say?